Okay, so in this newest lab, you have a video in which you can change the amount of hanging mass. So that's the amount of mass that's over here hanging over the side of the table. You could also change the system mass, but the system mass is the mass of the hanging mass plus the mass of the glider, and that's what I want you to hold constant. So the hanging mass can be changed. Load, okay. And then when I press play, the hanging mass will fall to the ground. So hanging mass is falling to the ground, and the glider is moving to the left, okay? So the glider and the hanging mass have the same acceleration because they're moving together as a system. And also, if I scroll back here before it hit the ground, okay, then the force of tension right here is the same as the force of tension right here because it's the same string, okay? So our hanging mass and our glider have the same acceleration. And also the force of tension applied to the glider and the force of tension applied to the hanging mass is also the same. So then every time that you change the hanging mass, you're changing the acceleration, okay? And then by using your ruler and your timer here, you can calculate the acceleration of the glider. So then if you take all of that over here and make yourself a force of gravity versus acceleration graph, so force of gravity for the hanging mass in newtons versus the acceleration meters per second squared, you should have gotten some sort of straight line. So then if I look at the equation of my line, so y is equal to our slope times x, then my y is the force of gravity of the hanging mass times the slope, and then x will be our acceleration. So if I look at the units for my slope, that is the force of gravity for the hanging mass over the acceleration, which is a Newton divided by a meter per second squared. And if you remember, a Newton is a kilogram multiplied by a meter per second squared. So really this is a kilogram multiplied by a meter per second squared divided by a meter per second squared. And when I do that, the meter per second squareds will cancel, and I'm left with the unit of a kilogram. So my slope here is some sort of mass, okay? And now we're getting a straight line, and so that means that my slope is constant, okay? So you were changing the force of gravity. So that can't be what my slope is. My mass of my hanging mass cannot be the slope. But the thing that you kept constant was the system mass, where the system mass was the mass of the hanger plus the mass of the glider. So for right now, force of gravity for the hanger is equal to the mass of the system, which again, one more time, is the mass of the glider plus the mass of the hanging mass on the side, times acceleration, okay? So I want to show you why this equation works, or why you ended up graphing that and how that becomes a true statement. So I'm going to start by looking at the free body diagram for my hanging mass and the free body diagram for the glider. Okay. So the glider would have a force of gravity, It will also have a normal force. And then the glider will have a force of tension from the string that it's attached to. I'm not going to put the force of friction on here because that lab setup is designed to be frictionless. So there was no friction in that video because that glider was on a track that was designed to be frictionless. So then if I go to the hanging mass, it has a force of tension and it also has a force of gravity. Okay, so now I'm going to sum my forces on both of them. So I'm going to sum my forces on the hanging mass, which I'll call mass 1, and the glider, which I'll call mass 2. The glider is moving to the left, sorry, and the hanging mass is moving down. So these objects are no longer in equilibrium. So when they were in equilibrium, the sum of our forces was equal to 0 because the force going up was equal to the force going down. But now that is not a true statement anymore. If I look at the sum of the forces in the y direction on mass 2, that is still equal to 0 because it's not moving up and down through the track, okay? So my normal force is still equal to my force of gravity. So I would have the normal force minus the force of gravity is equal to 0, okay? But when I go to sum my forces in the x direction, now instead of being equal to 0, it's going to be equal to ma because the glider is accelerating. So then my sum is only the force of tension because I don't have any other forces acting there. So force of tension is equal to mass 2 times acceleration. Okay. So then when I go to sum my forces in the y direction on mass 1, that's also going to be equal to ma because it's accelerating down towards the ground. Okay. And in order to sum these, you have two different options. So I'm going to go through both of them. The first one is leaving up as positive and down as negative. So that's been the coordinate system that we've used up until now, okay? And some of you may choose to keep that coordinate system, which is fine. So if I sum my forces based on that coordinate system, then force of tension is still positive, minus force of gravity, okay? But this object is speeding up towards the ground. So the object is moving in the negative direction, meaning that it has a negative velocity. And if you remember back to kinematics, for something to be speeding up, the velocity and the acceleration have to have the same sign. So if I have a negative velocity, then I need a negative acceleration to show that I am speeding up. Okay, so that's option 1. Or, and this second option is the way that I like to do it, I'm going to change my coordinate system. So coordinate systems are made up, okay? So I'm going to choose the direction of the motion to be positive. So I'm going to say that down is positive because it's moving down, which makes up negative. So then when I sum my forces, Fg would be positive, Ft would be negative, and I can leave this as m positive a because in this coordinate system, I'm moving down, which is the positive direction. So in order to show that I'm speeding up, I would need a positive acceleration. Both of these ways are the exact same. So whichever one makes more sense to you, that's the one that you need to choose, okay? So the first one, I kept the classic up positive and down negative coordinate system, but the object was speeding up, so I had to make my acceleration negative to match my negative velocity. In the second one, I made the direction of the motion positive, and since I was moving in the positive direction, that meant I had a positive velocity, therefore I need a positive acceleration. But mathematically, this first equation and this second equation are identical. So I'm going to use the second one moving forward, because like I said, that's the way that I like to do it, but you choose whichever one makes you happy, okay? So now I'm going to take the two equations I have here, this FG1 minus FT is equal to M1A, and then FT is equal to M2A, and I'm going to combine them together. So that tells me that FG1 minus M2A, so I'm just replacing force of tension with M2A because they're equal to each other, is equal to M1A, or FG1 is equal to M1A plus M2A, or force of gravity 1 is equal to M1 plus M2 times A, okay? And M1 plus M2 would be the system mass. It would be the mass of the glider plus the mass of the hanger. So this right here is saying that FG hanger is equal to the mass of the system times acceleration, which matches our equation up here for our graph, okay? So that's what you graphed. You graphed both of those equations combined together, okay? So now, I'm calling this Newton's second law lab because Newton's second law is this sum of the forces is equal to ma. So two things that I know. Sum of the forces is equal to 0. Didn't mean to write A, I meant to write 0, okay? And this happens when acceleration is 0. So that means you're either not moving or you're moving at a constant speed. The sum of the forces is equal to ma when acceleration does not equal 0. So these are your two base equations that you're working with right now, okay? So make sure when you're solving these questions, you are drawing a free body diagram. So first step, free body diagram. Second step, sum your forces. You need to be doing this for every single question, okay? And the sum of your forces is your equation. So when you take the sum of your forces and set it equal to 0, or you set it equal to ma, you're setting yourself up with the equation to answer the question. So really the only thing memorizable, if you can't see me, I'm doing some air quotes here, is this, is that the sum of the forces is equal to 0 or it's equal to ma. All of the sums of your forces are specific to each scenario. Okay, so keep that in mind as you move forward. Don't forget that when you have a positive velocity and a positive acceleration, or a negative velocity and a negative acceleration, you are speeding up. Or when you have a positive velocity, a negative acceleration, or a negative velocity and a positive acceleration, you are slowing down. So when you're using Newton's second law, or the sum of the forces is equal to ma, you have to look at your scenario, decide, am I speeding up or am I slowing down? Okay. And then if you're speeding up, you have to make sure you have your velocity and accelerations match, either both positive or both negative. Or if you're slowing down, you have to make sure they have opposite signs. So one positive and one negative, okay? So let me know if you have any questions. Use this to help yourself solve the example set number 3.